let's go right in. Essentially, a hypertable is like a normal Postgres table, but with automatic time and sometimes space partitioning plus some extra functionality, and TimescaleDB manages all of it for you, which is really convenient. So hypertables are really the basis for why TimescaleDB is able to be so efficient when working with time series data. So each hypertable is made up of what we call chunks, and chunks are an important concept to get comfortable with because so many of our functions and policies really work on a chunk by chunk basis. So important concept, definitely you want to dig in to understanding chunks. So these chunks are essentially child tables inside of the larger hypertable. And how we actually break up your data into these chunks is based on time, and specifically the time column in your data. So since I always learn best from examples, let's consider this example. So let's say that you have data collected over 3 days. So this is what the normal Postgres table might look like. So if you wanted to take this table and instead kind of create a hypertable so you could optimize on that time series efficiency, let's say that your hypertable had a chunk time interval of 1 day. So that chunk time interval essentially specifies how TimescaleDB is creating those chunks for your hypertable. So with a chunk time interval of 1 day, that would mean that each chunk within our hypertable will only contain data that occurs over a 1 day period. So each chunk has only a 1 day interval for it. So that's because our chunk time interval is 1 day. Makes sense, right? So then this image is really what that is showing. So right on the left, we have our normal table like we saw, and it has all of our data kind of together in one big lump, while a hypertable, which is on the right, partitions each value into specific chunks, and in this case, having each day's data in separate chunks. So we see, right, January 2nd, all of the readings from January 2nd are being mapped, or they would be kind of in a chunk of its own. So that's the chunk ID of 1. So that chunk ID 1 is for all January 2nd readings. That chunk ID 2 is for all the January 3rd readings, and so on and so forth. So that's kind of how the chunks work within hypertables. And by separating out the data in this way, or partitioning by time, the system is able to do a lot less work when you query, insert, delete, or update data by time. Say you want to query data from a single day rather than the system having to scan an entire table to find those specific values. With hypertables, the system knows exactly which chunk to go to grab and either look for or grab that information. So it's a lot faster. It kind of gives it a blueprint of where your data is based on time, which makes your system more efficient. Now, this was a very brief explanation. So if you are interested in learning more and want to get more comfortable with hypertables and chunks, definitely check out the links that we provided below, because they can be really helpful in just getting more comfortable with all that. So let's actually create some hypertables. While the concepts behind hypertables can be a little daunting, creating them is actually really easy, which is awesome. So the data set that we're going to be using for this Getting Started series is stock data, and it consists of 2 tables. So the first table is second by second stock trading data for the top 100 most traded symbols. And then the other is company information that maps those 100 most traded symbols to their actual company names. So those are the 2 tables. The stock trade table, we are going to transform into a hypertable because, right, it's second by second stock trading data. That's going to be a ton of time series data that we want to, make as efficient as possible when we query from it. So we're going to make that into a hypertable. And then the company table, we're actually just going to leave as a regular Postgres table. So let's go ahead and set these tables up. We're going to start off with the hypertable because I know that that's really what you're all here for. So to do that, we first just create a regular Postgres table. So we're going to go ahead and use this command. So create table. We name our table stocks real time. Okay, and then we have 4 columns that we're going to specify for this table. The first one is time, which is a timestamp time zone column. And we do specify not null. So with hypertables, it is a requirement that the time partitioning column is not null. If you don't specify it here, TimescaleDB will put that constraint on when you kind of transform it into a hypertable. But it's easiest to just throw it in now, I figure. So next we have symbol, and that's going to be a text column. Then we have price, which is a double precision, and day volume, which is going to be an integer, and specified not null or null for whichever one. So once we run that, we have a lovely normal Postgres table. And you might be wondering, well, then how do we create a hypertable? Well, it is super simple. All we need to do is just run this next command. It is truly just a select statement, which is great. It's super awesome. So this create hypertable function is a special timescale DB function which transforms your normal tables into a hypertable. And there are additional arguments that you can put into here when you create your hypertable, like chunk time interval, which is what we mentioned before briefly. I'm just going to use all the defaults, but definitely check it out if you want to maybe specify some of the parameters around your hypertable more specifically. So cool beans. And in addition, since I likely am going to be querying a lot by the company symbol, I'm also going to add an index on the company symbol as well. So I'm going to go ahead and run this command to create the index on the symbol column as well. And boom, once we run that, we have a hypertable and additional indexing, which is awesome. So then next, all we need to do is just create the second table for our company information. And to do this, we just run the following command. So we have create table company is the name of the table with 2 columns. We have symbol, and that's going to be text, right? It should mirror exactly the symbol column of the stocks real time table. And then the second column is going to be the name, and that will also be text, and that's just the name of the company. And there you have it. So we have our tables. Well, what's next? We insert data into our tables. And that's exactly what we're going to be covering in the next video in this series. If you want to make sure not to miss that video or any of the awesome content coming from Timescale DB, you'll want to smash that subscribe button. And if this video is helpful or useful, or if you enjoyed it, whatever, we always appreciate any likes and comments below as well. Thank you so much for spending your time watching this video today. Hello friends and welcome once again. In our last video, we had you create 2 tables, right? And now let's actually ingest data into these tables and into our TimescaleDB database. Before we jump right in, I do want to give a quick overview of the data that we're using just one more time. I know I mentioned a little bit of it last video, but it's always good to have a refresher. So the data that we're going to be ingesting today is stock data. And this data is very generously provided by 12 Data. So if you want to use more stock data than what we kind of give you a taste of, definitely check out 12 Data. They have awesome stock data packages and things like that you can check out. So check them out for sure. We have links in below as well. And then the data itself is actually 2 tables. And so, right, the 2 tables that we set up that are already, we have a stock table, which is tick level or second by second stock trading data, and then a company table, which maps the symbols in the stock trading table to a company name. So we can identify things a little bit easier. And then the last thing about this data set is that it is actually up to date. We tried something new. So this is the first time that we're doing this with one of our data sets that we provide on the timescale documentation. But the zip file that we're going to download is going to provide 1 month of data up to date anytime that you download it, which is really awesome. I know that we were very excited about that because, you know, having up-to-date data is just really useful and fun. So now that we kind of did that brief overview, let's jump right on over to the desktop and actually get this data into our database. So first, we want to hop on over to the Add Time Series Data Docs page. So if we go there, we can find the zipped data file. So we're going to go ahead and download that. And then we want to unzip the folder. So I'm going to do it in the command line using this command, but you can totally do it manually too if you want. So no problems there. Cool beans, we have it unzipped. So now we can actually copy them over into our database. Exciting. So if you are using a Docker container, I do want to go over one extra step here. So hang tight, cloud folks. We did bookmark this if you really want to skip it, but it's really fast. So for folks that are using a Docker container instance of Timescale DB, we first need to place the data files from your local machine into your container. So how to do this is that we just open a terminal, a separate terminal. I'm just going to use the same one that I used to unzip the files, but I'm just going to run these two commands, and that just copies the CSV files from my local machine onto my container. And then that's it. So the Docker CP command is what copies the files from your machine. The first CSV is the file location and name of your local CSV file. And then the last part shows the Docker container name, and then as the left portion, and then the CSV files to be location and name within your container. So that's kind of what that is. So then once we do that, back to what everyone gets to do, Docker and cloud folks alike. Next, we can actually copy the data. So for this, I'm going to use a terminal connection since I find it a little bit easier instead of a third-party tool. So I'm going to use the terminal to do this. And so once I have an open connection to the database, all I need to do is run these two lines of code. So that /copy is saying copy into our stocks real-time table within our database from this tutorial sample tick CSV file. on our machine or in our container. So we're going to copy stuff from that CSV into our table. And then we just specify some CSV parameters to make sure that the data ingests correctly. So might as well explain these two commands, since it takes a little bit of time to ingest all the stocks data, because it is a lot of data, even a month's worth of
In our last video, we have yourself, and this third-party library makes our work a bit simple. Our headers are now our keys.
my second stock data is quite a bit. So once that is finally done, boom, we got it ingested, the tables are populated, and we are ready to analyze. Woohoo! So we have data in, mash that subscribe button. And as always, friends,
Hello and welcome. The advantage of distributed systems and containers. And here I'm gonna set the hyper option that is required is the using Kubernetes.
So I thought to check how much concept have you grabbed, or how much have you understood from the past videos. So this is a really good exercise that we are going to do today. You can consider it as a mock interview, you can consider it as anything, but what you will do,
and then connect them.
Their actual deployments were small and the applications were managed across VMs. But the problem is that as New York Times became more of a digital company, they started building more digital solutions. And at some point, they realized that what they needed to do was to embrace the cloud and move all their solutions to the cloud. However, their first step of using the cloud, and this is, I think, typical for a lot of companies, is that they treated the cloud-hosted provider in the same way as they would with a data center. And at some point, they realized they had to take a change. And this is where the development team came in and they said, look, how about we stop thinking of our solutions as a data center, even though they're being run in Amazon, and start thinking of them as cloud first solutions. And so what they proposed and what they ended up doing was using
with the cluster. We will run the command equals to nginx. Pod name tree, and you can check the status using the. Now, as we discussed, a pod is the most basic and the smallest unit in Kubernetes. So we will be anything. Nginx started since it provides a lot more information as compared to the. In this demo, we're going to install a basic Kubernetes cluster using the mini. It is set up chmod plus X to make it execute. We're going to install mini Kubernetes cluster for yours. Completed, and once that has been done, let us add minikube to our path. The user local bin directory has already been created, so we don't have to do that first step. So let's open this link and make sure that we are using the correct driver name. So the name of a VirtualBox driver is VirtualBox. So we'll make use of that name. So I'm going to release of Kubernetes, and it should list the deployment will be in a terminating state for a few seconds. And after it's done, the application will no longer be accessible on the web page. Well, that's it for now. And I will see you in the next lecture. Earlier of deploying a cluster using minikube, then you already have have the kubectl command is in a registry, and we see that there is a ready column which shows the number of. In this demo, except for the increases available, the cube control direct download. The mini cube constraints now, but a single node cluster, and the node name is minikube, and it is in a ready state. And it was spun up about 8 seconds ago, and it's running the latest release of Kubernetes, which is 1.18 as of this recording. So next, let us try to create some deployments using this cluster. So here we have an example on this page. I'm going to run kubectl create deployment command to create the deployment. Once that is done, we will run the kubectl get deployments command, and you can see that the hello minikube deployment has been running for 22 seconds. Next, we will expose this deployment as a service. For that, make use of this command here, and kubectl expose deployment hello minikube command. Now don't worry about the command for now. We'll talk about this in much detail later in this course. For now, we'll just copy and paste. Okay, and then we will skip to step 5, where we will get the URL of the exposed service. So by running this command, copy the URL and paste it into a browser on your laptop, and it should list the details about the application like this. Okay, so that's not the most exciting application, but this is proof that your setup is working, and that's all we need for now. Now follow the remaining instructions to clean up your system, delete the services and delete the deployment. The deployment will be in a terminating state for a few seconds. And after it's done, the application will no longer be accessible on the web page. Well, that's it for now, and I will see you in the next lecture. Earlier of deploying a cluster using Minikube, then you already have the kubectl command line utility configured to work with the cluster. We will run the command kubectl run nginx, which is the name of the pod, -- image equals to nginx. Now here is where we specify the Docker image to be used. While the pod name could be anything, the image name has to be the name of an image available at Docker Hub or any other container registry. You can additionally specify a tag for the image name or a different address to an image hosted on another registry if the image is hosted in a place that's other than Docker Hub. Okay, so once we run this command, we see a pod by the name nginx has been created, and you can check the status using the kubectl get pods command. Now here you can see the column name, which is nginx, the status is running, and we see that there is a ready column which shows the number of containers in a ready state. We also see if the container has restarted since it was created and how long has the pod been running. We can get more information related to the pod by running the kubectl describe pod nginx command. And you'll notice that this provides a lot more information as compared to the get command. So for example, the name of the pod is nginx. It shows any labels that has been assigned to this pod. So this was created by default when we ran the run command. It shows when it was started. It shows the node that it is assigned to, along with the IP address of the node. So in this case, we just have a single node cluster set up using Minikube, and the node name is Minikube, and that is the IP address of this worker node. Secondly, it also shows the IP address of the pod itself. So in this case, the pod is assigned an IP of 172.16.0.3. We'll cover more about the IP addresses of the pod later in the networking section. Now moving on, we can see that it displays information related to the container. So we know that there is a single container which uses the image nginx. If there were multiple containers, we would list them here. I'll explain about creating a pod with multiple containers in the upcoming lectures. But here we can also see that the Nginx image was pulled from Docker Hub. And if you scroll all the way to the bottom, you'll see additional information called events. And here you see the list of events that occurred since the pod was created. It went through multiple stages before it started. We can see that the pod was assigned to the Minikube node. If there were multiple nodes, you would see which node the pod was assigned to here, and then it entered the pulling phase where the Nginx image was pulled down from Docker Hub successfully, and then the container called Nginx was created and started. Now there is one other command that we can use to check the status of the pod, and that is the same command as before, the kubectl get pods command, but with the -wide option. And this provides additional information such as the node where the pod is running and the IP address of the pod as well. So this is the internal IP address of the pod itself. So each pod gets an internal IP of its own within the Kubernetes cluster, but more on that later. That was a quick demonstration on how to run a pod in Minikube environment. In the upcoming videos, we will see how to create a pod using a YAML definition. Hello and welcome to this lecture in a Kubernetes. Kubectl commands are working. So I'm going to run the kubectl get node deployment hello minikube command. Now follow the remaining earlier of deploying a cluster using Minikube, the cluster Nginx. Now here is where we specify the Docker image to be used, or any other on another region. The kubectl has the pod itself. So now moving. Hello and welcome to this lecture. In this lecture, we take a look at what YAML files are. If you are familiar with YAML already, feel free to skip this section and head over to the next section. If you have not worked with YAML in the past, I would highly recommend going through this because the rest of the course depends entirely on YAML. If you have worked with other data structure formats like XML or JSON, you should be able to easily pick it up. Don't worry if you haven't worked on any of these, you should still be able to easily pick it up going through the coding exercises that accompany this course. A YAML file is used to represent data, in this case configuration data. Here is a quick comparison of a sample data in 3 different formats. The one on the left is XML, where we display a list of servers and their information. The same data is represented in JSON format in the middle, and finally in YAML format to the right. Take a minute to compare the 3 formats. Let's take a close look at YAML. If you take the data in its simplest form, such as key-value pair, this is how you would define it in YAML. Key and value separated by a colon. The keys are fruit, vegetable, liquid, and meat, and the values are apple, carrot, water, and chicken. Remember, you must have a space followed by a colon differentiating the key and the value. Let's take a look at how an array is represented. We would like to list some fruits and vegetables. We would say fruits followed by a colon. On the next line, enter each item with a dash in the front. The dash indicates that it's an element of an array. How about a dictionary? A dictionary is a set of properties grouped together under an item. Here we try to represent nutrition information of 2 fruits. The calories, fat, and carbs are different for each fruit. Notice the blank space before each item. You must have equal number of blank spaces before the properties of a single item, so they are all aligned together. Let's take a closer look at spaces in YAML. Here we have a dictionary representing the nutrition information of banana. The total amount of calories, fat, and carbs are shown. Notice the number of spaces before each property that indicates these key value pairs fall within banana. But what if we had extra spaces for fat and carbs? Then they will fall under calories and thus become properties of calories, which doesn't make any sense. This will result in a syntax error which will tell you that mapping values are not allowed here because calories already have a value set which is 105. You can either set a direct value or a hash map. You cannot have both. So the number of spaces before each property is key in YAML. You must ensure they're in the right form to represent your data correctly. Let's take it to another level. You can have lists containing dictionaries containing lists. In this case, I have a list of fruits and the elements of the list are banana and grape. But each of these elements are further dictionaries containing nutrition information. A lot of students new to YAML have reached out to me asking when to use a dictionary or a list. So let me explain this a little bit better. First of all, it is important to understand that all of what we discussed so far, such as XML, JSON, or YAML, are used to represent data. It could be data about an organization and all of its employees and their personal details, or it could be data about a school and all of its students and their grades, or it could be data about
Hey, it's Rencode here, and today I'm going to showcase how we can call an REST API from
about an automobile manufacturing company and all of its cars and its details. It could be anything. Let's take an example of a car. A car is a single object, and it has properties such as color, model, transition, and price. To store different information or properties of a single object, we use a dictionary. In this simple dictionary, I have properties of the car defined in a key value format. This need not be as simple as this. For example, in case we need to split the model further into model name and make year, you could then represent this as a dictionary within another dictionary. In this case, the single value of model is now replaced by a small dictionary with two properties, name and year. So this is a dictionary within another dictionary. Let's say we would like to store the name of 6 cars. The names are formed by the color and the model of the car.
Everybody, I hope you can hear me. Let me just jump.
Hi everyone, my name is Ryan Booz. I'm a developer advocate here at Timescale. And for Timescale Tuesday today, I want to show you how you can use the informational views and functions we provide for hypertables and chunks to query a number of things that might be useful to your situation. Specifically, I'm going to show you how you can query the various views and functions together to get details about the size of your hypertables and chunks as you start to use more and more of the features within Timescale. Hopefully you can take that and then extrapolate it to maybe. Hi everyone, my name is Ryan Booz. I'm a developer advocate here at Timescale. And for Timescale Tuesday, I'd like to talk to you about a new
Hello and welcome friends. In this video, we are going to be looking at compression. Setting up compression can help you save a lot on storage costs, and in many cases, it can speed up your historical queries. So say it is, you want tables takes 3 different parameters. Timescaledb.compress, which is required, and this enables compression on the hypertable. Then we have timescaledb.compress order by, which are columns that are used to order. So since we likely want to query our stocks table based on compression like this, so we want to
If you have a microservices architecture on your backend, your services are most likely integrated and can communicate with each other in one way or another. To test this integration between the services, you or your team most likely uses end-to-end tests, which can be a bad choice for many reasons. First of all, end-to-end tests are very slow. You need to spin up all dependent services. These dependencies bring flakiness. Debugging that flakiness becomes a nightmare. You need to read the logs of your cluster to find out which services actually errored out. Not to mention all the services you'd have to set up for different scenarios. And last but not least, how on earth can you know the test coverage of your microservices communication? This is a common issue in many real-world situations. At eBay, a team called Notification Platform faced exactly the same challenge. The challenge of maintaining compatibility with all consumer and provider APIs. In this scope, a consumer service is the one that requests data, while provider responds to the consumer. To address this, they adopted contract testing and built tools to integrate the consumer-driven contract testing workflow into eBay's development ecosystem. But we're gonna dive into that in a minute. I hope you find this case study educational and learn a couple new things for yourself. Just a quick reminder though, your likes and super thanks really help me keep this channel going, so I would really appreciate if you do that. And if you want to support this channel and be notified about new videos, you know what to do. And now let's get started. So eBay's main goal was to find a reliable way of evolving APIs with backward compatibility. Since their APIs were based on the Open API specification, they evaluated the possibility of ensuring API compatibility via Open API schema evolution with semantic versioning. This approach is wholly managed by the service provider. For example, even if renaming a data attribute in response wouldn't break the consumer's data consumption or deserialization, we still need to be conservative in making such change, as we don't know whether a consumer uses this particular data attribute. So the Open API specification on its own doesn't really reflect how the API consumers depend on the schemas. This solution also doesn't address the fragility of the end-to-end testing problem. So they had to find a way to make the consumer's requirement more formal, just like in the provider's API specification. They first looked at the behavior-driven development, basically an approach of writing consumer tests with the intended behavior of the API in mind. Collaboratively defined by the API consumers and providers, they could now implement provider-side test cases to cover the verification of the behaviors in the unit test. This seemed to fill the information gap between the consumer and provider. But what if the consumer changes the requirements without updating the behavioral specification? What if the consumer and provider APIs are maintained by completely separate teams that don't have many touch points with each other within the organization? Using BDD to ensure API backward compatibility still largely relies on the human interactions of developers who are performing this process. So eBay couldn't take this as the final solution. Given these flaws, they turned to contract testing. The usual contract testing goes like this. Let's say you have two microservices, a booking service and a payment service. The booking service wants to fetch the payment details, so it's going to be the consumer, while the payment service is the provider of that data. The collection of HTTP interactions that are going to happen between these two services is called a contract. So in our simple example of a single query, it's going to be an HTTP call to the payment endpoint with an ID, and we're going to get back some data like this. The biggest benefit of contract testing is revealed here. In a scenario where we do integration testing, or worse, end-to-end testing to test that our microservices work as intended, we issue a request from a consumer to a provider, and this provider can have its own provider, and that provider can have its own provider, and suddenly we have a black box with a dependency chain. In contract testing, however, we never have those things talking to each other. We're only testing one service at a time, and we're going to capture the consumer's view of the integration test with the provider. So step one is testing the consumer, and that's where we capture the contract. And what we do is we let the consumer talk to the mock that our contract testing framework provides. So we make a request for the payment details and we get some response. Then we repeat this process for all the needed interactions that the consumer would also use in a real production environment against the payment service, aka the provider. So in this step, the framework is going to check that the consumer does all the intended requests correctly and that it can handle the returned response. If one of the tests fails, then the contract hasn't been fulfilled by the consumer and the CI/CD pipeline shouldn't succeed. As a step 2, these interactions are going to be recorded and forwarded to a broker who plays a key role in helping us with automating these tests. Now the broker is going to share these tests with the provider. It's going to replay the request that it captured from the consumer, but this time against the provider's API. This is where we verify the previous contract by expecting the predefined responses to be returned from the payment service. The cool thing is that the framework is smart enough to know how many consumers this provider has, and it's going to run all of them in a batch. If the data returned matches our expectations, then the contract is fulfilled. And we can be pretty confident that the communication between our microservices is stable. The generated contract is then shared across teams so that they can include it in their own CI/CD pipelines. Here's a very quick overview of the code for contract testing of our use case. So in our example, we're going to be using Pact, a framework that we're going to look into in a minute. But basically, it simplifies everything. So in consumer spec.js, since our tests are consumer-driven contract tests, we're going to define our consumer, booking API, and provider as well. And this is the controller method that we want to mock. We're fetching the payment details from the payment API while being the booking API is the consumer, right? So we defined all the needed parameters. This is the URL that we're going to be fetching, and this is the expected response that we want to get from the payment API. So we're going to describe it here that payment ID 1, if we make a call to this endpoint, we're gonna get a 200, and provider that accepts a request with this data, which is basically this controller here, is going to respond with this data, which is again the expected body. And this is it. This is the contract for one of our endpoints, okay? And the provider, what it does, it basically takes the JSON file that gets generated after you run your consumer.spec.js, and it takes this JSON file, which is basically the contract between the booking and the payment service, and it's going to verify this. How does it verify? Well, first of all, it starts the payment service. This is a typical design of a payment system. Now, most places that you go, you're going to see something similar. And actually, there are some points that can make this system less robust and quite flaky. We're going to go over these points. Here's a quick sneak peek, and we're going to talk about the remedies. and how to mitigate the impact of these issues. All right. Now, before we do that, I think it's very important to first dive deep into the design itself and understand how components interact with each other, because here we have different kind of services, databases, and payment providers, and so on. So we're gonna do all of that within this video. So if you're ready, let's get started. So this is a typical summary page of your e-commerce platform where the users would end up before making their purchase. So after they click the buy button, a lot of things are going to happen. First of all, we're going to create a payment event. And notice that I'm using the word event here because it kind of signifies that our whole backend architecture is actually an event-driven architecture. I'm going to talk about this in details in the second video that comes after that. But for now, just remember that there's a lot of asynchronous stuff happening in the backend. All right. So the payment service that you see here is actually the central service that's also going to interact with a lot of components. But first of all, what it does, it creates a payment order. The payment order is basically a list with the buyer ID here, with the IDs of items that are being purchased, with a timestamp of the creation, and we're going to save it in our own database. But after that, we're going to forward this payment order to a payment service provider, known also as PSP. So Stripe, for example, is one of the payment service providers. Its direct responsibility is to basically move money from one account into other account. And it may or may not also contact the card scheme based on whether this account is directly linked to some kind of a credit card. If not, it's not going to do that. All right. So now that we know how the heavy lifting is done by the payment service provider, also notice that we have this dotted line here. So to the left of this dotted line, all the components are internal. So we have direct control over them. On the right hand side, we don't have much control because everything here is external. And you probably noticed that we also have these colorful lines because this is exactly what we're going to talk about this. And we're going to start with the second one, meaning the processing delays. The processing delays is actually very crucial because you also probably experience the fact that the payment service provider takes a while to complete the payment. So we have two options to mitigate that. How we can do this is, first of all, make sure to use long polling. So long polling is when the payment service provider is going to tell our payment service that, hey, your request has been accepted. So it's a 202 HTTP response, but it also gives a polling URL, meaning we can tell the browser, hey, your request has been accepted, but please check this URL from time to time to basically check the status of the payment, whether it's completed, whether it's still processing, and based on that, show something to the user, right? This is a very common pattern because also Microsoft supports this fully in their API design page. I also made a video about this, so you can check it out. But basically, we're going to return 202 accepted with the polling URL, and it's going to either show completed or failed, and you can try various retry techniques that you like. But coming back to our Blackboard, we also have this green line, which is a webhook. You're probably familiar with that. So whenever we're registering the payment order with the PSP knows that, hey, there's some kind of a webhook that I need to call upon completion, and the call is going to be registered with the payment service. So now the payment service knows that the payment has been completed and it's going to show a different page to the customer. All right. So these are two techniques that we can use: long polling and webhook to mitigate processing delays and very slow processing by PSPs. So you probably noticed that this payment service provider here is actually playing a very important role in our payment system. All right. Not only it's responsible for moving money from one account to another, but it directly correlates with the fact whether we can let our users pay with their credit cards. Maybe we can also let them pay by PayPal, or maybe we can also let them pay by cryptocurrency, because I'm pretty sure most of us are using cryptocurrencies or own cryptocurrencies. And I think it's a no-brainer to let your customers also pay by cryptocurrencies. And that's why I want to give a shout. Now we discussed processing delays, let's go back to reconciliation, our first point. So what is reconciliation? So as you can see here, we have a ledger and user wallet. And as soon as the payment has finished, the payment service actually asynchronously has to update the ledger. Ledger is basically where all the transactions have been saved, so meaning the debit and credit records. And we have the user wallet, where the funds of the specific user are saved. It can be an internal, but it can also be a bank account directly, depending on the architecture. And they have respective database, meaning these
We ensure that our solution has a fully reliable infrastructure from data aggregation, processing, storing, and feeding to the customer. We made it affordable for the SME architecture overview. So what we do, we have customers from different profiles, like smart buildings, we have IoT asset owners and power plants. So we aggregate real-time data, process it at the mobile app and analytics platform, which can be integrated with any third-party hardware, because we know that hardware is not something that is defensible and can be scaled easily. So we work with Huawei Schneider with our platform, and we use basically deal with solar and wind power plants, but then we expanded to smart building solutions, AI-based solution to the smart buildings in Singapore domain, fresh. A lot of solar assets that we're managing. It's quite a lot for a young company like us. We have more than 17 to the building management system, energy management. Share a few things later on the. So we work mainly with enterprises. We charge them one-time. These are some of our customers side. Myself and my co-founder, we both coming from energy backgrounds. We are one of the portfolio companies of Entrepreneur First. That's where we spinned off. I did my 4.5 years as an R&D engineer. I have a background in microorganization, and I think we have around 30 seconds. So I'll share why we got recent interest from the government entities in Singapore. We were featured a few weeks back as part of the CNA documentary on climate change in Singapore. So we did a small pilot run with 3 families in Singapore, where we installed our solution in a household and showed how our solution helped them to save the electricity. And each of the households saved around 20 to 40% of their energy in that month when we installed. And then we got interest from HDB in a huge tender process where we're partnering with Aztec and Yokogawa. Then we got the interest from MOE, where they want